How are elements formed? This question varies for different elements, but our focus is on elements that are naturally occurring and not man-made. The lightest and most abundant elements in the universe, hydrogen and helium, were created in the aftermath of the Big Bang, or the rapid expansion of space that created our universe. Hydrogen and helium make up most of the matter in stars, including our Sun. Other elements can be formed through fusion and fission, often in stars. When a star is in its main sequence, it is hot enough that the kinetic energy of the protons of its hydrogen atoms can overcome their electrostatic repulsion, so hydrogen is fused into helium. For most stars, this is through the proton-proton chain, a series of thermonuclear reactions occurring in low and mid-mass stars like our own Sun. In the proton-proton chain, 4 hydrogen nuclei fuse into helium, also forming a positron, gamma ray, and neutrino. More massive stars use the CNO cycle. 4 protons fuse and use carbon, nitrogen, and oxygen isotopes as catalysts, which are regenerated in later steps. The product is a stable helium nucleus, as well as 2 positrons and 2 electron neutrinos. Once a star exhausts its hydrogen supply, it begins to fuse helium instead in the triple alpha process. 3 helium-4 nuclei are transformed into carbon, and at this point the star is a red giant and begins to form layers like an onion as it fuses even heavier elements. Carbon fuses into magnesium, and once carbon is depleted, the star switches to fusing neon, and then it starts to fuse oxygen, and then it begins to fuse silicon. Iron begins to accumulate in the core of the star. Silicon burning is the last stage of nuclear fusion in stars, where fusion is exothermic. The star cannot fuse iron, which is built up in the core, because the fusion reaction of iron and elements heavier than iron is endothermic. It's endothermic because for such elements, overcoming the electrostatic repulsion of a large number of tightly bound protons in the nuclei requires more energy than what is released by nuclear attraction. Therefore, the fusion of iron is endothermic, while the fission of elements heavier than iron, or the breaking down of those atoms into smaller elements, is exothermic. This is reflected by the iron peak, a local maximum in the abundances of elements. Element abundances also reflect other trends, such as the Otto-Harkins rule, which states that elements with odd-numbered amounts of protons are less common. We see this pattern in element abundances because each step of the triple alpha process for fusing hydrogen into helium adds 2 protons to atomic nuclei, thus favoring formation of even-numbered elements. Elements heavier than iron are not fused in the cores of stars, but there are still other ways they can be formed. The remaining iron core of a star becomes a white dwarf, which, if massive enough, may collapse into a supernova. Supernovae may also occur when white dwarfs and binary systems spiral into each other and collide, or accumulate enough mass through some other method. The shockwave of the explosion carries enough energy that it can fuel the creation of elements heavier than iron in neutron capture reactions called the S process and R process. In these reactions, neutrons collide with the atom's nucleus, forming a heavier nucleus. Another way in which elements heavier than iron may be formed is through the merger of neutron stars, which are remnants of very massive stars that are even denser than white dwarfs and are essentially just balls of neutrons. This explosion is called a kilonova and can power the creation of very heavy elements, especially gold and platinum. It is believed that most gold and platinum is formed from kilonova explosions. The elements fused in stars in these stellar explosions eventually join the interstellar medium, which is collected in molecular clouds. And in these molecular clouds, stars and planets like that of our own solar system and Earth are eventually formed. And as humans, we are made up of numerous elements, the lasting remains of fusion in stars and dusty stellar explosions. That means that you and I and our planet are composed of the matter that has been recycled in and out of stars and supernovae and kilonovae. Indeed, as Carl Sagan once said, we are made of star stuff.